So in this video, we're going to look at so-called crystal polyhedra, or maybe even a better way to phrase this would be crystal coordination polyhedra, because we're going to look at the so-called coordinations of various elements in a given crystal. And the crystal that we're going to use as an example is the mineral olivine from this very nice diagram from Klein and Dutro, their mineralogy textbook. So olivine has this composition, Mg, Fe, and then a subscript 2 SiO4. So just for a little bit of review, the common means we can take any combination of magnesium and iron we like, so long as it adds up to 2 when we've got 1 silicon and 4 oxygens. So we can have magnesium at 1.5, and then iron at 0.5, or we could switch those numbers. And you might object, we can't have half of an atom of iron. Well, it's not saying that we have half of an atom. This is really a recipe. So all it is telling us the proportions of materials that we need, the proportions of the elements that we need to be able to make olivine. It just says you need 2 of these kinds of divalent cations, and it doesn't matter what combination you take them. And that would be per 1 atom of silicon and 4 atoms of oxygen. What this diagram does down here is it shows how they are arranged. With some simple metals, the atoms, especially the oxygens, could be in some kind of simple closed packed structure that in another video we talk about. We describe these as HCP or CCP, and we'll save that for another video. Well, these oxygens are not arranged that way. The silicon-oxygen bonds are highly covalent, and those highly covalent, highly directional bonds means it's not so easy to make something that looks like this. So we don't have a closed packed structure of the oxygens. The oxygens, by the way, are going to be here at the corners. Anywhere you see a corner, that's going to be an oxygen atom. Let's take a look at this guy here. We call it the silica tetrahedron. And so it's a tetrahedron that by definition it has 4 sides, right? So tetra, and then hedron. This is from the Greek. Tetra means 4. And so hedron just means that we've got something that has 4 sides. We'll draw a little line in the back. So we've got a little 3-sided pyramid up top, and then another 4th side down here at the bottom. And inside in the middle of that fellow would be a silicon atom. So a silicon would go in there. So the silicon over here would fit into the middle of that fellow, or equivalently this guy, or that one, or this one. So we'll just put T's next to all of these. These are the so-called tetrahedra. Notice that some are pointing up. The way they're shaded indicates that that little oxygen that is at that corner there is facing towards us. The dashed lines here show that this guy is pointing downwards. It's going to look the same. These are effectively equivalent sites, except that that tetrahedra here is pointing up towards us, and this one is pointing down. So that's where the silicons go. And there's another thing called Pauling's rules and radius ratios, where you can show that because the silicon atom is so small, the silicon 4+ atom is only going to go in the tetrahedral sites and not these larger M1 and M2, which we'll talk about next. The silicon atom is so small it would just rattle around, and one of the ideas behind Linus Pauling's rules is the so-called no rattle rule. So we don't want atoms rattling around in a large space. So the silicon is only going to go there, and we need to look at Pauling's rules and radius ratios to figure out why. So how about the M1 and M2? Those are both octahedra. So let's spell that out. Octahedra. Octa means 8. Again, we have an 8-sided thing using the translation from the Greek. So you can imagine we've got 1, 2, 3, and then a 4th side in back, a little 4-sided pyramid up here, and then out of the field of view is another 4-sided pyramid. So it's kind of a little double 4-sided pyramid. It gives us 8 sides all together. What is the coordination of the fellow that goes in there? It is 6. So if we have an atom that's bonded to, let's say, 1, 2, 3, 4, 5, 6, we can see that we can draw an octahedron if we connect all of the various oxygens that occur on the corners. That's a very sloppy square here. It's meant to look more like this. So we've got a square, and then a tetrahedron there, and then another tetrahedron below. So that's our octahedra. And interestingly enough, we have to be careful when we talk about coordination. These fellows, the magnesium and iron, are surrounded by 6 atoms. So when we draw Roman numeral 6, here we mean that it is in contact with 6 oxygens, whereas the silicon is in contact with 4. So this 4 coordination number gives us a 4-sided figure, but this 6-fold coordination, which we can write this way, 6-fold coordination, gives us an 8-sided figure. So you have to be a little bit careful about mixing and matching the values for the coordination number and then the number of sides that we get on a polyhedron. Sometimes those numbers match, sometimes they do not. Why do we have 2 octahedra, an M1 and an M2? Because there are 2 distinct sites. I'm going to erase this, but you can go back to take a look at this to see what we mean. So for the M1 site and the M2 site, you'll notice that the M2 is a little bit larger. And so if we know, for example, that iron, let's say the radius of iron is also a little bit larger than the radius of magnesium, you might then guess that magnesium would have a preference for the M1, while iron would have a preference for the M2. That's not a hard and fast rule. Iron can go in either M1 or M2, and Mg can go into both of these as well, especially at high temperatures. And it's one of the ways we can calculate calibrate a thermometer. We could look at the way magnesium and iron atoms are distributed between the various M1 and M2 sites. If there's a high degree of separation where most of the magnesium is here and most of the iron is here, that perhaps means that the mineral formed at very low temperatures. Whereas if we have magnesium scattered about both sites and iron scattered about both sites, that might indicate that we have high temperatures. The temperatures are so high, the atoms have enough energy to jump from one site to the other, and they're not really settled into just the M1 or just the M2. Anyway, if you go back and rewind the video, you could take a look at that figure, and that's basically a map. You can think of it as a map of where the atoms go for olivine. It's not showing us the bonds, it's not showing us the atoms. Instead, it's showing the various polyhedra in which magnesium, iron, and silicon, in this case being the other cation that we've discussed, will all fit into the structure. So it's a very unique way of talking about crystal structures and a very helpful way of having a map and trying to figure out where various atoms will go. And so for that reason, you'll see it quite a bit when people talk about mineral structures.